Hey everyone, and welcome to this explainer. Today, we're going to decode the absolute alphabet soup of acronyms that took our chaotic, old school factory floors and turned them into these perfectly synchronized digital ecosystems. I mean, think about it. Every complex gadget you own, from that smartphone in your pocket to the car sitting in your driveway, was born out of organizing this exact kind of chaos. So, if you've ever found yourself wondering how modern manufacturing pulls off producing such insanely complex items with that mind-bending speed and precision, you are definitely in the right place. We're going to untangle the invisible digital threads that tie this whole thing together.
Okay, to set the stage, let's dive into a frankly staggering manufacturing challenge. Imagine for a second being tasked with designing and building a massive commercial airliner. Historically, that meant building huge, incredibly expensive physical mock-ups just to see if all the parts actually, fit together. But what if you didn't build a single prototype? What if you relied entirely on a totally paperless design? Well, that is literally exactly what Boeing did with the 777. The entire airplane was developed on computers, zero physical mock-ups. Now, the price tag for that development was a cool $6 billion, but it proved, on a massive, unprecedented scale, the sheer power of digital manufacturing systems. They linked 2,000 workstations to 8 computers, and the plane was essentially built directly from the software. It's just a perfect example of the magic that happens when design and manufacturing are totally integrated. To see how achievements like that are even possible, we'll walk through a logical 5-step journey today. We'll start with part 1, the integrated factory brain, then look at part 2, designing the digital twin. After that, we'll move on to part 3, planning the production, then part 4, computer-aided execution, and wrap it all up with part 5, the group technology advantage. Let's get right into it. Starting at the very top, part 1. The integrated factory brain, and how we manage volatility and complexity. Because let's be real, manufacturing is a highly volatile beast. You've got constantly shifting global markets, raw material costs bouncing all over the place, supply chain nightmares, and, of course, human error. To juggle all of that at once, an organization absolutely demands a smart, lightning-fast central system. And at the very core of that is CIM, Computer Integrated Manufacturing. Think of CIM as the central nervous system, the actual brain of the factory. We're not just talking about some robots on an assembly line here. It's the total integration of the organization's entire operation, connecting absolutely everything through a massive shared database. So if a raw material suddenly spikes in price, the CIM system instantly knows, and it helps the whole company pivot on a dime. And here is how that builds into a living, breathing ecosystem. CIM relies on these interconnected subsystems. The real genius here, the output of one subsystem automatically becomes the input for the very next one. The business planners forecast the schedule, which feeds directly into the design, which informs process planning, straight down to the automated machines on the floor, and finally into the monitoring systems that feed all that sweet data right back to the top. It's a gorgeous, continuous closed loop. But hey, before we ever cut a single piece of metal, we have to conceptualize it. That brings us to section 2, designing the digital twin, where we tackle physical constraints in a purely digital space. Enter CAD, or computer-aided design. Now, CAD allows engineers to quickly conceptualize an object, tweak designs, run through alternatives, and even test for things like excessive loads or parts crashing into each other, all on a screen. Instead of the old days of drafting by hand and just crossing your fingers that parts fit on the floor, CAD acts as this amazing, risk-free playground for engineers. What's really fascinating about this 4-stage CAD process is just how exhaustive the digital review is. First up, geometric modeling. We mathematically represent the object. Second, we blast it with intense engineering tests, checking stress, heat, vibration, you name it. Third is the design review, essentially making sure moving parts don't smash into one another. And finally, we lock it into a database, meaning standard parts like specific gears or bolts can just be instantly pulled up for the next big project. Which leads perfectly to one of the most brilliant features in modern CAD, the parametric solid model. With parametric design, you aren't just drawing static, fixed lines. You are establishing mathematical relationships between the dimensions. So, say you need to scale a part up by 10% for a new product line. You just tweak the core parameter and boom, the entire 3D model automatically adjusts to keep its exact proportions. It makes updating designs ridiculously fast and cost-effective. All right, so we've got our perfect digital twin. But we can't just toss that file at a machine and magically get a finished product. Making that jump to the real world takes some serious coordination, which brings us to step 3, planning the production, essentially the blueprint for making.
This is where CAP steps up, computer-aided process planning. Back in the day, process planners literally hand-wrote these routing sheets that physically traveled alongside the parts around the factory, telling people what machine to use and for how long. CAP entirely replaces that manual nightmare. It automatically documents standard times, machines, and operational sequences in a centralized file. It looks at the whole factory as one integrated machine to find the absolute most efficient path.
Now, within CAP, you've generally got two distinct flavors. And notice the stark contrast here. A variant system is kind of like a super organized digital filing cabinet. It scans the new part's code, finds a similar older part in the database, pulls up that old plan, and says, "Here, just tweak this." Generative systems, on the other hand, far more advanced. They act almost like an AI, using deep decision logic to write completely optimized, brand new plans from scratch, based purely on the geometry and what the factory can handle.
And hovering above CAP, acting as the ultimate boss, is the ERP, the Enterprise Resource Planning System. If CIM is the brain of the factory floor, ERP is the brain of the entire global business. It manages the whole shebang: employee schedules, global supply chains, taking customer orders, and finally triggering the actual factory production. It's the system handing down the high-level marching orders to the manufacturing execution layers below. So now we reach the physical culmination of all that intense planning. The process plan is locked, the ERP has given the green light, and the baton is finally passed to the hardware. Let's look at part 4, computer-aided execution, turning those digital plans into hard physical reality. CAM, or computer-aided manufacturing, takes the wheel here. CAM grabs that flawless geometry straight from the CAD database and calculates the ultra-precise toolpaths for the computer numerical control machines. And because it's translating the data directly, it completely eliminates human manual entry errors. You don't have an operator out there typing in coordinates by hand, risking a catastrophic sparks-flying machine crash. The computer just flawlessly translates the design into physical movement.
Okay, so we've covered the software side heavily, but how do we physically organize these incredibly fast machines to actually keep up? We'll see how factories physically optimize themselves in our final section, Part 5, the Group Technology Advantage, reorganizing the factory floor. Making this work requires a methodology called Group Technology, or GT. GT is all about spotting the similarities. Imagine a factory turning out 3,000 different unique parts. By analyzing them, they might suddenly realize, wait, 90% of these parts actually just fall into 5 major families, like a family of shafts or a family of seals. By classifying parts into these families based on design or manufacturing steps, factories can finally stop treating every single piece like a unique snowflake and start standardizing the flow. The real-world impact of group technology is like night and day. In the old functional layout, all your layers were crammed in one room, all the drills in another. A single part would have to zigzag chaotically back and forth across the entire building, just wasting a staggering amount of time. But with a group layout, which you might hear called cellular manufacturing, machines of different types are clustered together into a single, dedicated cell, built specifically to produce one family of parts. It transforms a random, chaotic maze into a sleek, incredibly streamlined powerhouse.
And when you link the whole system together, CAD for design, CAM for execution, and group technology for the physical layout, the advantages are just off the charts. You wipe out design duplication. A brand new junior engineer can instantly leverage a master process plan from the database. Setup times completely plummet because the machines are already configured for that specific part family. Manufacturers are seeing mind-blowing savings, ranging anywhere from 5% to 75% across different phases. It's gotten to the point where custom, small batch production can actually rival the sheer efficiency of massive, traditional assembly lines.
Which really brings us to the bleeding edge of where all this is heading. We are fast approaching a reality where consumer e-commerce interfaces directly, completely seamlessly with enterprise resource planning. So I'll leave you with this provocative thought about the future of fully integrated manufacturing. How soon will we see a world where your single click on a website autonomously awakens a machine tool halfway across the globe? It's wild to think about. Thank you so much for joining me for this explainer, and keep looking out for the invisible systems that build our world.